Hey guys, so this lesson is called Derivatives of Logarithmic Functions. So it says, now let's move on to calculus properties of log and exponential functions. So the theorem is for x being greater than 0, f of x equals log base b of x is continuous and differentiable. Further, the derivative of log base b of x will equal 1 all over x, like that x, times ln of b. And an example would be if they ask you guys to take the derivative of log base b of x, it would end up giving you 1 all over x ln of 3. Now it says, note that an immediate corollary to this is if y were to equal like ln of x, then dy dx, or the derivative of that, would just be 1 over x. And then they're saying, well, why? Well, if we kind of follow the same pattern of what they're showing in that example, so like if you start with d dx of ln of x, ln of x can be rewritten as a log. It's just log base e of x. So now carrying out the derivative when it looks like that, you would have 1 all over x ln of e, and ln of e actually just equals 1. So you get x times 1, or 1 over x. And that's like why when you guys take the derivative of ln of x, it ends up just being 1 over x. When you do log of like a base that has a number, you still are going to have like that 1 over x happen, but then you got to times the bottom by that ln of whatever the base is. Okay? So then if it says, so down here, further, we often use the chain rule in conjunction with differentiating logarithmic functions. Thus, we have the following. So now they're doing like log base b of a function. So when that happens, you have to do 1 all over, and it's just going to give you like 1 all over f of x. But then you got to times it by ln of whatever the base is, the b. And then since it's a function, you want to think of it kind of like chain rule, and you still have to multiply by the derivative of the function that they give you. So then the same thing kind of holds true for ln of a function instead of x. It's going to now be 1 over the function instead of 1 over x. But then you got to times by the derivative of the function. Okay, so again, when a function's in there, not just an x, that's kind of the thought process. So let's just try a bunch of these, okay? So example 1. The derivative of this would just be, if I want, I'll just call it dy dx. That would be 1 all over x ln of 3, and then that's it. We just stop. Okay, the next one, now that I have to do with chain rule, right, because it's a function taken to a function. So I'm going to bring the 4 out in front, right? Then do x plus log base 7 of x to the 3rd, right? So all I did is picture this as like a big giant x. If I take the derivative of x to the 4th, I get 4x cubed. Okay, I'm just leaving the function in there. But then I got to times it by the derivative of that function. So derivative of x is 1, and then I got to add that to the derivative of log base 7 of x, which would be 1 all over x ln of 7. And that would be my final answer. Okay, so then the next one, the outside function's ln of x, so I know that I just do 1 over whatever this function is to start. But then I got to times it by the derivative of that function. So derivative of sine is just cosine. So then I end up getting cosine of x over sine of x, which we know is just cotan of x. So then the next one, same process, dy dx would equal 1 all over the function. But then I got to multiply by the derivative of the function. So derivative of tan of 4x would be secant squared 4x. But since 4x is in for x, I still got to multiply by the derivative of 4x, which is 4. So that's like a double chain rule because I technically have 3 functions. I have 4x, tan of x, and ln of x. Okay. And then all I did was I took a line and just rewrote it better. So like 4 secant squared 4x all over tan of 4x. And I just left it like that. Okay. Now the next one, if you guys see a division thing like this, we are actually allowed to use log properties to solve this. So since this is division, I can rewrite it as subtraction. So I'm going to do that before I differentiate. So log base 10 of x squared minus 1 minus log base 10 of x. So now that I have it looking like that, I can take each one individually. So for this one, I would have 1 over, so it's over the function, so x squared minus 1 times ln of the base, which is 10. But then since there's a function, I got to multiply by the derivative of that function, which would be 2x. And then this one's going to be 1 over x ln of 10. And I just stopped there with that one. Okay, so then turn the page. So then it says, sometimes a rule of logarithms can help simplify the calculation, as in the following examples. Okay, so in other words, like for this one, it might make sense to try to change this into an exponent such as ln of 5x plus 7 to the 1/2. And then with my log rules, I can move the 1/2 to the front because it's an exponent. And now I have this. That's a lot easier for me to differentiate now. So if I differentiate it, dy dx, the constant comes for the ride. The derivative of ln of that would be 1 over the function, right, times the derivative of that function, which would just be 5. So rewriting it a little neater, I would have 5 all over 2 times 5x plus 7. Okay. The next one, I would want to do product rule, or think of it like product rule. And think of it like that function times that function. So dy dx, I would do x as is times the derivative of ln of x. So that would be 1 over the function ln of x times the derivative of ln of x, which is just 1 over x. So that plus ln of x times the derivative of x, which is just a 1. And then I just, again, took a line. This would be, these x's actually cancel. So it would be 1 over ln of x plus ln of x. And I just left that one like that. Okay. The next one, I would probably also think about it like product rule, where I'm going to look at that function and then that function. Okay, so let's see. dy dx would be x as is. The derivative of this is with chain rule. So I'm going to bring the 3 in the front, keep this as is squared, and then times it by the derivative of the inside. So I would have 3 log base 2 of x squared minus 2x quantity squared times the derivative of the inside. So that's going to be 1 over the function times ln of the base, which is a 2. And then you got to times by the derivative of the inside, which is 2x minus 2. Okay, that was kind of a lot. So then all of that plus, now you're going to keep this the same. So log base 2 of x squared minus 2x cubed. Derivative of x is just 1. Okay, and I'm not going to go any further than that. You guys kind of get the gist. So then the next one is just this example actually has come up on 2 secured exams that I've seen before. It says the function y equals x ln of x minus 4x is a solution to the differential equation. Then they give you this like equation to check. So I show the work that leads to your answer. So this is what you do. You're going to find the derivative of y, okay? Because you already have regular y. So if you find the derivative of y, this is product rule in the front. So x as is, derivative ln of x is 1 over x. That plus ln of x as is, times the derivative of x is 1. Derivative of 4x is just a 4. Okay, so then take a line. These cancel, just give you 1 plus ln of x minus 4. So I get ln of x minus 3 when all is said and done. Okay, so this is what I'm going to do. I'm going to take this equation, and what I do is I sub in y, the original function in for y, this one in for y prime, and if this side cancels to be 0 or equal like this solution they're asking for, then it's a solution. Okay, so it's kind of a weird question, but this is the process. So I'm going to sub everything in. And then now it's all arithmetic. Distribute that. So you're going to see that it cancels, right? So that's gone. X minus 4x plus a 3x is 0. So you get a 0 equals 0. So when that happens, you're just going to say yes, x ln of x minus 4x is a solution. Okay, and that's the easiest way to check that. So one more example. Now this was an actual exam question that I pulled, and it's kind of detailed, so don't write big when you're copying the notes. If you printed them, if you have a notebook, right, obviously it doesn't matter. It says, let f be the function given by f of x equals, and then they give us that. And then they give us a domain. So they first want us to find the x coordinate of each relative max point and each relative min point. So the easiest way to do that, the max and min, is the first derivative test. So I'm going to start with finding f prime. Okay, so if I find the derivative of this, the 2 comes for the right because it's just a constant. Derivative of ln of that is going to be, let's see, I'm going to have 1 over the function times the derivative of the bottom. Derivative of negative x is negative 1. And then I just, again, rewrote it better. Okay. So I'm going to check a couple things. I want, well, I pretty much need to know where it's undefined and where it equals 0. So I'm going to start with undefined. Now, since we have a fraction, right, I can't let that equal 0. However, when I do this, I get like a no solution, like scenario. Okay. So now I'm going to do it over here. So now I got to check for f prime of x equaling 0. So this one's a little, I don't want to say harder, but annoying. So what I'm going to do is add 1. And then what I could do is cross multiply, right? So then I would have 4x is equal to x squared plus 3. And then now I'm seeing it's a quadratic, so I'm going to put it all the one side. Okay, factor it. T solve, and I get 3 and 1. Okay. So what I would do from that point is I would do my test points. Now, I kind of ran out of room. Actually, here, I'll flip this paper over. So you're going to do this. Now, they only want it between -3 and 5. So you don't want to test, like, say, like -4, because it's not in the domain they gave. So you're testing this in the first derivative because it's the first derivative test. And again, guys, I know you know how to check this, so I'm just going to give you these numbers. Okay, so you get it, f is decreasing, then increasing, then decreasing. So because of that, you're going to have a relative min. Now, they wanted just the x coordinate is going to be at x equals 1. That's because it's going decreasing to increasing. And then you would have a relative max at x equals 3 because it's increasing then decreasing there on f. Okay, so that was to answer the first question. So now part B says find the x coordinate of each inflection point. Well, we know we get inflection points by our second derivative test. So now doing the second derivative, I know, like, when I take the derivative of 1, it'll be gone. So I really am just going to think of quotient rule right now. Okay, so doing quotient rule, it's the denominator as is times the derivative of the numerator minus the numerator as is times the derivative of the denominator all over the denominator squared. Okay, simplifying that, I get 4x squared plus 12 minus 8x squared all over, and I'm going to keep the bottom factored so it's easier to solve later. So I get, let's see, negative 4x squared plus 12 all over x squared plus 3 quantity squared. So where is it undefined? The same situation's happening. It's never going to be undefined. So you could write f double prime undefined. Not possible because we already showed it on A. So I don't want to waste time with that. So now my second derivative, though, equaling 0, I need just the top of this fraction to equal 0 for it to equal 0. So I'm going to set negative 4x squared plus 12 equal to 0. I could subtract 12. Divide by negative 4. Square root it. And I get plus and minus square root of 3. So when I check the second one, again, my domain's from negative 3 to 5, but then I got to check from negative square root of 3 to square root of 3. And it ends up going negative, positive, negative when you sub it into the second derivative. So you have inflection points technically at both of those points. So inflection points at x equals plus and minus radical 3. Okay, and then the last one, find the absolute max of f of x on the given domain. So what we're going to do is just pull our critical points from part A. So 1 and 3. And we test f at the endpoints and the critical points. So our endpoints of our domain are negative 3 and 5. Our critical points from like our first derivative test are 1 and 3. So I'm just going to sub it all into the original f of x function. And I'm just going to write these out. So I believe ln of numbers, so when you're looking at this right away, it's kind of hard to tell, but you can kind of do some process of elimination without a calculator, because you know that obviously like f of -3 is bigger than f of 3 because this one adds 3 to it. And then you know that this one's got to be bigger than ln of 4. So you're down to these two. So I did have to verify this in the calculator, but this ended up being the max value when I checked it. And I think it's because if you think of what L of n looks like, it like kind of teeters off. Like the further it goes, it looks like that. So I feel like these ln of 12 and ln of 28 are very like minor differences in the scheme of things. So by subtracting 5 to it versus adding 3, this one ends up being bigger. So the absolute max value is whatever 2 ln of 12 plus 3 is, and I'm just going to leave it exact. That's it, guys. Okay, thanks.